Introduction. Our research question was, how does changing the current affect the speed of the motor? We hypothesized that an increase in current within a circuit will increase the number of rotations the wire loop makes within a specific amount of time. And some of the findings we expect to see were increasing the number of batteries in our system proportionally increases the current through the loop. Increasing the current through the loop linearly increases the number of rotations it makes within a certain time frame, and increasing the current through the loop increases the magnetic force applied to the loop.
Our system schema includes the electrons in the wire loop, a battery, and a magnet. There is a magnetic interaction between the electrons in the loop and the magnet, and there is an electric interaction between the electrons and the battery. Our circuit diagram details 3 batteries shown, but our model actually ranged from 1 to 5 batteries. It labels the current flow and the magnetic field direction generated by the magnet, as well as the induced magnetic field generated by the moving current. In order to allow the wire to flip, only one side of one end of the wire should be stripped, while the other can remain fully stripped. The magnetic forces shown in the figure in situation 1 will be canceled out as the loop flips to position 2A if the wire is not shielded to prevent the current from generating the opposing forces. If we shield the wire from current flow for half of the rotation, the momentum from the first half of the flip will allow it to complete the flip and re-establish current flow. Is a magnetic force. They are orthogonal to each other, so it can be determined by the second right-hand rule. Moving charges can experience the same force to which they contribute, so this aids in moving the wire loop. And according to Newton's second law, the force acting upon an object is dependent on its mass and acceleration. So if we increase the force acting on the loop, this will increase its acceleration as long as the mass remains constant.
For our experimental design, we changed the number of batteries in our circuit, and then we measured the number of rotations completed in 3 seconds. For our procedure, we stripped one side of the wire completely, and then we left the other side of the loop halfway stripped. We then attached the alligator wires to the loop as well as to 1 to 5 batteries, and we recorded with an iPhone for 3 seconds.
We considered 2 equations for our experiment, Ohm's law and magnetic force. Due to lack of current measurements, we represented an increase in current as an increase in voltage. According to Ohm's law, as long as we assume the resistance to remain constant, an increase in voltage will proportionally increase current. Since we demonstrated an increase in current and our permanent magnetic field and wire length remain constant, the increase in current will result in an increase in the force exerted on the wire.
And now it's time for data and results. On the left-hand side of the slide, as you can see, we have a table which consists of our voltage and our average number of rotations per second, which was found using the videos that were recorded in class. And on the right side, you can see there is a positive proportional relationship between voltage and loop speed, as depicted by the graph that was created. As voltage increases, so does the average number of rotations per second.
The loop rotation occurred due to the permanent magnetic field produced by the magnets and the intermittent circuit flow as previously described. We wanted to know, why will increasing the current increase the number of rotations per second? Well, we know that force equals current times length plus the magnetic field. Therefore, as you increase current, you will increase your force, assuming length and magnetic field remain constant. We also know that force equals mass times acceleration. Therefore, if you increase force, you will increase acceleration, assuming that mass remains constant. Some flaws we noticed were we did not measure the current. We noticed that magnetic field produced by the loop, as well as friction due to air resistance, were not taken into account. And then the iPhone shutter speed may not have been fast enough to catch all rotations. We also had only 1 trial recorded.
So the setups were the same for our in-class setup and our DC motor. They both have a power source, a wire coil, and a magnet. In the DC motor, the coil feels an electromagnetic force, which our in-class setup did as well, leading to both of their rotations. Our in-class setup lacked commutator rings, unlike the DC motor, so there is a lack of propulsion within it, and a stronger current will flow through the DC motor powering the toy.